Okay, let's start. Good afternoon. First of all, about the tutorial. So, do you have any problem in the do you have any problem in register for tutorial group? No, huh? I think right now we have 10 tutorial groups, and I think the Tuesday 4 to 5 is very popular, almost full. We intend to open another 4. So we'll let you know or make the announcement. So if for those who have not registered, so try to register online. If you want to do transfer, I don't know whether you can do it online or not, transfer from one group to the newly opened available tutorial groups. If you can't do it online, then let us know. Then we'll try to do it manually. Tutorial start next week. Tutorial questions have already uploaded, so you can start working on it. All right, but you may need what we discussed today. Okay, so last week we talked about combination and permutation. So now we really apply those rules to some practical problems, sort of practical. Okay, so here is example 1. So we have a box consists of 25 good stuff and 5 not so good, the apples, right? And we want to know how many samples of 5 that we can select from this box. Now, basically, it's like a selection, like a combinatoric or a combination problem. Okay, so what you need to do is to identify, okay, how many items are available for you to choose. So in this case, if we don't have any restriction, we don't distinguish between good and bad apples, then altogether there are 30 items that you're going to select. All right? We presume that these apples are not the same. Okay, you can number it from 1 to 30. So how many ways that you can select? All right? So first of all, we figure out how many samples of 5 that you can select. So there are altogether 30 items available. So for this one, so we have altogether, we have 25 plus 5 items. So in this case, we try to choose 5 out of 30 of them because we are going to choose 5 apples. This is just any 5 items from these 30 items. So this is the number of ways that we can choose. All right? So n equals 30 items, we select 5. So the answer is 142,506. All right? So it's quite straightforward. Now, how about B? Question part B. How many of samples in A involved exactly 1 bad apple? All right. Now, in this case, we have some condition applied to our selection. We want to have only exactly 1 bad apple in the sample. So now I have to separate these 30 apples into 2 groups. One is the good apples and the other is the bad apples. All right? So at first, we have 30 and we just take a sample of 5. Now we divide this 30 into 2 groups. One is 25. Why 25? Because we have 25 good apples and 5 bad apples. So from these 5 bad apples, all right, you have to select 1, not more. not less, but 1 bad apples. Then, in order to form a sample of 5, you need to select 4 from these 25 good apples to form a sample of 5 apples. All right? Then how to link up these 2 choices? Because for each bad apple that you choose, they are altogether choose 4 out of 25 good apples. So you have to apply the multiplication rule. For each choice of the bad apple from the 5 bad apples, you can have choose 4 out of 25 ways to choose the good apples. All right? So you have to apply the multiplication rule. You have to understand why we have to apply multiplication rule, because for each way that you choose a bad apple, there are so many ways that you can choose the good apples. How many ways? Choose 4 out of 25. Now, as a check, whenever you do this one, you check whether these 2 or whatever you have here, add up these 2 numbers, add up equal to the number of items available for you to choose. In this case, it's 30. And then the second entry here, all right, for each of the combinations, they have to add up equal to the number of ways that you can choose the 5. The number of or the sample size, let's put it this way, the number of items that you can choose. All right, so this add up to 30 and this add up to 4. Multiply them together. That is the answer for A. Then, how many samples in A involve at least 2 bad apples? Now you have to pay attention to these words. At least 2. At least 2 means that it can be 2, can be 3, can be 4, can be 5. Can it be 6? Can it be 6? At least 2. If I don't look at the problem, at least 2 means that 2, 3, 4, 5, 6, 7, 8, 9, 10. Any number greater than or equal to 2. But can it be 6? Of course, when I ask her, of course it cannot. But why? At least 2 what? Bad apples. How many bad apples do we have? 5. How can you have 6 bad apples out of 5 bad apples? All right? Yeah. So it is 2, 3, 4, and 5. So in other words, you have to look at how many samples, all right, of size 5 with 2 bad apples. So you just repeat what we have just done in part B, but we place the 1 by 2 and we place the 4 by 3. That means choose 2 bad apples from the group of 5 bad apples, choose 3 good apples from the 25 good apples. That is for the number of ways for getting 2 bad apples. And then you have to consider 3 bad apples and 4 bad apples and 5 bad apples. So altogether you have to calculate 4 of them. 2, 3, 4, 5. And then how to combine all these 4 number of ways to get 2, 3, 4, and 5 bad apples. Multiply them. What I'm trying to say is, all right, here. Choose 2 bad apples. So the other is 3 good apples, 3 bad apples, and 2 good apples. 4, 1, 5 bad apples, and 0 good apples. So after I compute all this, what to do next? Should I multiply them or should I add them? Add. Why? Or mutually exclusive, yes. Good. So it's a fancy word, mutually exclusive. So basically, if you have 2 bad apples, you cannot have 3 bad apples in the sample. So it must be one of this. When you look at a sample, it's either 2 bad apples, 3 bad apples, 4 bad apples or 5 bad apples. So you have to add all this number of ways to get the samples. All right, so that's one way to do it. But there's another way to do it. All right, another way to do it is the complement of it. What is it? That means we look at how many ways that you can form a sample of 5 with no bad apples. No, 0 bad apples. And then 1 bad apples. Do I consider bad apples? No. So I just consider 0. So 0 bad apples and 1 bad apples. So in other words, I will consider choose 5, 0, 25, 5, plus 5 choose 1, 25 choose 4. What does this sum represent? It represents the number of ways or number of samples of size 5 that with either 0 bad apples or 1 bad apples in it. Right? But this is not what I want. I want exactly the opposite, the complement of it. So I have to subtract this number from all possible samples that I can have. Because all possible samples of size 5 is either at least 2 bad apples or just 0 or 1 bad apples. So I have to subtract this from how many ways I can choose? 5 apples. 5 apples, not 5 bad apples. So I altogether 30, choose 5. This is the number of samples that I can have. Number of samples of 5, of size 5 that I can have. So subtract it. So that's an alternative. Okay, so I have 2 answers. I have 2 ways to get the answer. All right. So check whether the answer is correct. Whether the answers are the same. If they are not the same, then what to do? Ask your tutor. No. Okay, go and double check your calculation. The answer should be the same. Okay? There are only 2 possibilities. One is your computation is wrong. One of them is wrong, or both are wrong. All right? The other one is that your understanding or our understanding my explanation just now was wrong. All right? So I believe my approach should be the same. 2 ways to get the same answer. All right? So what's the moral of this example? Or this part C, you can have 2 ways to do things. Okay, you have 1 way to get the answer. Okay? Try to see whether you have another way to get the answers. All right? Or the 3rd way to get the answer. And if the answers are all the same, my confidence is almost 100% that I'm right. All right? Okay, if they're not the same, then either there's something wrong with the calculations or something wrong with the understanding of the different approaches. All right. So, better work on those. All right? Okay. Okay, I think I skipped example 2. You can read it yourself. Example 3. Example 3. So I want to form a committee. And the number of persons that involved are altogether 9 persons. 4 men and 5 women. All right? So the first is to form a committee. How many of them? 3. Size 3. So it's similar to the example 1. Example 1, we have 25 good apples and 5 bad apples. Here we have 4 men and 5 women. And we want to form a committee of size 3. All right? So, with no restriction, still have restriction. We're talking about choose a committee with size 3. So, altogether, we have 9 persons, we choose 3. So, this is the way that, this is the number of committee that we can form. Committee of size 3 that we can form from this 9 persons. Remember, here 9 persons, you can label them, all right? A, B, C, D, E, up to I. Without loss of generality, we assume A, B, C, D are the men, and then the rest are the women. All right? So Okay, part B, with 2 men and 1 woman, if a certain man must be on the committee. All right? Now, at the beginning, for part A, we have 9. We want to find how many ways that we can form a committee with 3. All right? So now, here, what are the conditions or what are the constraints applied to this committee? First of all, it's not any 3 persons. All right? There are some restrictions. So what are the restrictions for this committee, for part B? Can I have 3 women on the committee for part B? No. So in other words, we have a constraint, a condition that you have to satisfy. The condition is that you need to form the committee with 2 men and 1 woman. 1 woman. All right, so that is the first condition. Then the second condition is that a particular man, okay, must be on the committee. So in other words, there are conditions that we need to meet for this particular committee. So, according to these conditions, we divide the 9 persons into how many groups? First of all, this particular man, 1 group. Then, the remaining 3 men. Why I have to do that? Because I'm going to choose someone from each of these subgroups. So the other is 5 women. So I have to choose this one. Okay, I must choose this man. Must be in it. Then I have to choose from the 3 men to choose certain number of men. How many? So now I live with only 1 vacancy in this committee, which is for this man. So I have to pick 1 man from this remaining 3 men. So I have to choose 1. And then from the 5 women, I choose 1 woman. All right? So in other words, I divide these 9 persons into 3 groups, not just men and women, but into women and then 1 particular man as the second group or as a group, and then the third group or the remaining group are the remaining 3 men. So the number of ways to do it will be, I choose 1 man from the 1 particular man group, and then the remaining 3 men, I choose 1 man. And then I choose from the remaining, from the 5 women, I choose 1. Okay? Now you have to understand, first of all, why we multiply, because for each choice, there are so many other ways to choose, all right, to form this committee. Secondly, these numbers, 1, 3, 5, add up to 9, which is the original number of persons, and this 1 plus 1 plus 1 is the size of the committee. Okay, so it met this choose a size of 3. Not only that, I also choose 1 woman from this 5. So I met this part. All right? And I also choose this particular man. So I meet this criteria. And 2 men. So I have 2 men here. This add up to 2 men. Not only that, this basically means that it is considered choose 2 men from 4 men. All right? Choose 2 men from 4 men. But it's further divided, not just any 2 men, but a particular man must be in the committee. All right? So it's a subset of choose 2 men out of 4 men. All right? How about C? So for C, we have to work it in the opposite, in the complement way. So we still want 2 men and 1 woman, but 2 of the men are fielding and refuse to be in the committee. So that means Now, this one is hard. If you try to work out, these two men, all right, cannot be in the committee, which means that one of them can be on the committee. All right? Let's say A and B, for example. These two men represented by A and B. So it can be A on the committee, but B is not. Also, can be A not in committee, on the committee, and B is on the committee. Is that a third scenario? They don't want to be served on the same committee. Both are out. So there's another possibility that both A and B are not in the committee. So in other words, if you think it this way, then you have to work out these three scenarios. A in, B not in. A not in, B in. And both A and B are not in the committee, or on the committee. All right? So it's harder. So maybe easier is that to look at both A and B are on the committee. All right? So this is how we do it. So this is the number of ways that these two particular men so we choose 2 out of 2, 1 out of 5. Now I have a problem. And this one, the second entry, add up equal to the number of persons in the committee. That's 3. How about the first entry? 2 plus 5 is 7 there. I don't see any 7 there. I have 9 persons. So where are the two missing persons are? It's not in my formula. Huh? They just missing, right? Okay. We have 2 men, so there are altogether 4 men. These 4 men divide into 2 groups. These 2 particular men that suppose we are working on them, they refuse to work together, and there are 2 other men. So from this group of 2 other men, how many we choose? How many we choose? 0, 1, 2, 0? Of course, we don't choose anyone. Hey, if we choose any one of these 2 remaining men, then how about the other 2? I mean, we have only 2 places. If you fill 1, then left with only 1. We are considering these 2 men. These 2 particular men must be on the committee. Therefore, so we cannot let the other 2 men have any place in the committee. So now it's okay. 2 plus 2 plus 5 is 9. 9 persons. Divide into 3 groups. 5 women, 2 particular men, and 2 remaining men. From the 2 remaining group, we don't choose anyone. The 2 particular men all in. And then the 5 women choose 1. So that's how we do it. So maybe you like to add this. And you know what it means. Multiply. All right? So you have to understand what we're doing. We divide the 9 persons into 3 groups. 5 women, 2 particular men, and the 2 remaining men. From this group of 2 remaining men, we choose no one. The 2 particular men, both are in. And the 5 women, we choose 1. So that's the answer for number of ways to form a committee with these 2 men in. And then if we subtract this number from the total committee that we can form, then that will represent the number of committees formed, okay, with just one of them or none of them in the committee. So here's the answer, 25. All right? Okay, example 4. I think I skipped this one. Example 5 is quite straightforward. All right? It's basically saying that bridge hands. Bridge hands means, I don't know, bridge, you know what is bridge, right? So it's a deck of cards divided into 4 parts, and then there are two groups of players, they play in pairs, all right? And anyway, it's a hand of 13 cards. So we want to know how many ways that we can have 4 spades, 6 diamonds, 1 cup, and 2 hearts. All right? So in other words, we divide the deck of cards into 4 groups. Each group consists of 1 suit. Spade 1 group. How many are there? 13. And heart, diamond, and cup. Of course, there are 2 jokers, but we don't include the jokers. All right. So we only 52. So you can see that these numbers add up to 52. The number of cards in the deck of cards. 4 spades, 6 hearts, 1 diamond, 1 cup, and 2 hearts. 6 diamonds. So this is the number of ways to get this 4 spades, 6 diamonds, 1 cup, and 2 hearts. All right. Okay. So let's move on to talk about probability. But let's define probability first. All right. So there are quite a number of ways to define the probability. This one is based on what we call relative frequency. All right. It's slightly different from what you have learned in maybe in your JC or in your poly days. All right. What it says is that, okay, we have an experiment, and then we perform the experiment, and if an event A, all right, associated with this experiment occur, then we record down and redo the experiment again and see whether event A occurs or not. So basically, we do a number of times of the experiment, let's say 1 million times, all right, and then look at how many times of the experiments that give you an event A, and take the ratio, the relative frequency. That means the number of times that the event A occurs over the number of experiments that you do. So basically, it is NA over N. N is the number of times you perform the experiments, while NA is the number of times that the event A has occurred out of this N experiment. So obviously, what can we say about NA and N? How they are related? How are they related? Can NA bigger than N? No. You perform N experiments, how can you have NA which is bigger than N? The number of occurrences is bigger than the number of experiments that you do. All right. So this is the relative close. So this number must be between 0 and 1. Between 0 and 1. All right? Because NA cannot be bigger than N. At most it's N. And NA cannot be negative. At most it's 0. 0 means that it never show up in the N times that you perform the experiment. All right? So, you see? FA has to be between 0 and 1. FA equal 1 means that every time you perform, all right, event A occurs. Do we have such event? Very simple. Like if I toss a coin, 2 possible outcomes, head or tail. If my event is head or tail, no matter what you throw, it always happens, head or tail. Or maybe you just toss a die, 1, 2, 3, 4, 5, 6. If my event A is 1, 2, 3, 4, 5, or 6, then you toss a coin and toss a die. Outcome is 3. Event A occurred. All right. If you toss it again, you got a 6. Event A occurred because my event A is 1, 2, 3, 4, 5, 6. So every time you perform the experiment, event A has occurred. On the other hand, if my event A is saying that got a number 7 in toss a coin, toss a die, no 7. Toss again, no 7. So the chance of this event occur is 0. All right? And if A and B are two mutually exclusive events, then the relative frequency of this union event, A or B occurs, basically is just to add f of A and f of B. All right? This is provided that these two are mutually exclusive. And this is how we link the relative frequency approach to the traditional or classical approach of finding the probability. That is, the relative frequency should stabilize. So what I mean is that, like, for example, toss a die. What's the chance getting a 6? We know that for a fair die, it should be 1/6. 1 out of the 6 equally likely outcomes. But if you toss a die, out of 100 times, you may not have exactly 16.6 times of 1. All right? So you may have 18 times or 20 times of 1s out of 100 times. But if you perform more and more times, like 1 million times, then the relative frequency should be very close to 1/6. I will not say that it's exactly equal to 1/6, but it is close to 1/6. So that's what we mean by stabilized. So the FA will fluctuate, especially when your n is small, like 100, 200. Then you don't expect that will be very stable. But as n getting, okay, what I'm saying is that, okay, like toss a die, I want to know what is the probability getting a 1, for example. Then it will be like this. This is the number of times that I perform the experiments. If you perform it one time, I just toss it. Okay, I'm talking about f of 1, all right, which means that f of A is equal to getting a 1, all right? So toss one time. So what is the relative frequency? It may be just 1, if you happen to be got 1. Or maybe if it's 2, 3, 4, 5, 6, then it is 0. So your experiment, you may have something which is either 0 or 1. But then as you perform, as n getting bigger and bigger, what I mean is that it may go like this. Then it will stabilize at the value 1/6. That means we're close to 1/6 as n getting bigger and bigger. So that's what we mean by stabilize. Okay, so here is the mathematical part. Mathematics, axioms of probability. Axioms. This is the foundation. Everyone believes that. We don't challenge that. We accept it as the golden rule. So the rest of what you understand or you know can be derived from these axioms. All right? So what are these axioms? So for an event, the probability of an event is between 0 and 1. All right? And the second axiom is that the probability of the sample space. Remember what is sample space? Sample space is the collection of all the sample points, all the possible outcomes. All right? So it has to be equal to 1. Now the third one is a little bit hard. It's saying that if you have infinite number of mutually exclusive events, A1, A2 up to A something, all right, cannot stop. It's infinity. So the union of it, of all this, all right, is an event. This is an event. All right, this is an event. And the probability of this event turns out to be the sum. This means the sum of probability of A1 plus probability of A2 plus probability of AK. I cannot stop there. I still have to continue plus. It means that it never stop, all right, go to infinity. So the point is the sum of the probabilities of an event, which is a union or combining all the mutually exclusive event AI, then the probability of this new event is the same as the sum of the probabilities. Sum of the probabilities of each individual event. We can do that, or we can make it work, or this axiom is reasonable, is that because they're mutually exclusive. All right, so AI occur or not, all right, if AI occur, then AJ will not occur. So I can add up all these probabilities together to get the union of all these events. Okay, so here is some example to illustrate how we derive the probabilities based on these three axioms. Okay, so consider toss a coin, and H is having a head. So what is the probability of having a head? So in this case, it's understood that we are looking at the sample space, which consists of head and tail, two sample points. So what is the probability of H? If it's a fair coin, it is a fair coin. All right. So we want to find what is probability of having a head. Everyone knows it's half, right? If it's fair coin, but why? So we try to derive it based on these three axioms. Okay. So it's very simple. First of all, probability of S equal to 1, the axiom 2. So in other words, probability of H union T, this is the sample space, is equal to 1. All right? So that's axiom 2. Then what to do next? Then probability of H union T is equal to probability of H plus probability of T. Right? It's not exactly the axiom 3, because axiom 3 talk about infinite union of infinite exclusive set, mutually exclusive events. We just have 2, but it still applies. We can show that axiom 3 can derive, we can derive a probability of union of finite mutually exclusive events. We don't need infinite finite. So in particular, we have only 2 mutually exclusive events. Their union equal to the sample space, and they are mutually exclusive. If you got a head, you won't get a tail. All right? So that is what we can do based on the axioms. Then how to get the probability of H? So here we have to use not from the axioms, but from the question. It's a fair coin. What does fair mean? Fair means that these 2 are the same. So you just replace. That means you are solving 2 equations. All right. The first equation is this one, because this one equal to 1. The second equation is not from the axioms, but probability of H equal probability of T. So we have 2 equations, two unknowns, probability of H and probability of T. Fair coin get us the second equation. So solving 2 equations with 2 unknowns, the answer is half. All right. Then the second part B, now the coin is biased, a head is twice as likely as tail. So which means that for part B, we replace this by the probability of getting a head is equal to, and where should I put the 2? Twice. Probability of, so I put a 2 here or put it here? This is bigger. Getting a head is more likely. How likely? Twice as the probability of tail. So this is the second equation. Substitute in and solve the equations. 2 equations for part B. All right? So that's how you get the answers. So 2/3 getting a head. You see, the computation is so easy you can guess, all right? Twice, so probably the head is 2/3. But I want you to understand these are based on the axioms of probability plus the information or the condition given in the question, and then we derive it. So I set up two equations for two unknowns. Probability of head, probability of tails. Don't assume that they are always equal. All right? Only for fair con, then they are equal. So that is for fair con only. Otherwise, these are two unknowns. Probability of head and probability of tails are two unknowns. All right. I think example 2, example 3, you can read it yourself. All right. So let's look at the second part of chapter 1. Yes, here. Okay. Basic properties of probabilities. Now this one, basic properties. So all these properties, suppose, can be derived from the axioms of probabilities, the three axioms. So the first one, we know that probability of empty set is equal to 0. What does it mean? It means that probability of impossible event or null event is 0. But how to show that? From the, how can we derive it? So it's very simple. We let A1 equal empty set, A2 equal empty set. All right. So because each of these are empty set, so the intersection again is empty set. All right. All this A1 is empty, A2 empty. So what are the things in common? No elements are in, common to all this. So it's empty set. So it means that all these AIs are mutually exclusive. All right? And then the union of all this again is empty set. You have empty set, another empty set, a third empty set. You union all this, you still have nothing. All right? Right? If you have no money, your friend, no money. Together, also no money, right? So it's empty set. All right? Now, here is the magic. So we start with probability of the empty set. So this one, all right, we treat it as union of infinite number of AIs. All right? Because each AI is equal to empty set. Then here we apply the axioms 3. So we got this sum of the probabilities. Then we put that the AI are empty set. So we have sum of probability. We have an infinite sum. Each one is the probability of empty set. So in other words, we have probability of empty set equal probability of empty set plus probability of empty set plus and so on. Infinite number of them. How can the left-hand side equal to the right-hand side? Can the left-hand side, probability of empty set, only one probability, equal to the sum of a bunch of probability of empty set? Is it possible? Is it possible? Huh? Yes, it's possible only if and only if the probability of empty set is 0. Right? 0. Add another 0. Add another 0. It's still 0. So in other words, the solution for this equation, what is probability of empty set, is 0. Any number other than 0 will not give you the left-hand side equal to the right-hand side. So that's why the probability of empty set is 0. Okay? Okay, my point here is that we know intuitively probability of empty set, impossible event must be 0. But we can derive this statement from the axioms. All right? So that 3 axioms are the foundation of probabilities. And the other properties that you should know can always be derived from these 3 axioms. So this is just one. Second one, as I said, so now we are working instead of infinite unions, we just union n of the AIs. All right? And it happens that it's equal to the sum of all this probability of A1 up to probability of AN. And the proof is very simple. We just have to assume we consider adding an infinity, infinity, infinity to the rest. So it becomes an infinite number of events. All right? They are mutually exclusive. Why? These are mutually exclusive. This is what we assume. And then any one of these with any of the empty set, the intersection again is empty set. So they are mutually exclusive. So any pairs, any three of them, the intersection is again empty set. All right? So I just add. So suddenly I create, seems that instead of looking at A1 union A2 up to AN, now I add in some more sets. All right? But these are empty sets. All right? Remember, although I write it as an empty set symbol, but there's nothing there. All right? It's a set with nothing in it. Okay? So therefore, these two are equal, so the probability of these two events are the same. And by the axiom tree, so I have this one, all right? Then the rest, this one basically is probability of empty set, probability of empty set, and so on. All these are zero. So you're just left with this one. So in other words, axiom tree is a general case, including when you just union, an event which is union of all the finite union of AIs. And for any event A, probability of A complement is equal to 1 minus probability of A. So this is quite straightforward because A union A complement is the sample space and the intersection is empty set because they must be mutually exclusive. So therefore, this equal to this, and applying what we just do for the previous, the property 2, but n equal to 2, A and A complement. So property 2, we have A, A1 equal A, and A2 equal A complement. So it becomes like that. So therefore, this is 1. This one is 1. So probability of A complement is 1 minus probability of A. All right? So these are well-known facts. Now, again, this one is to apply what we just discussed. Basically, we rewrite A equal to union of two mutually exclusive events. And this is very simple technique. I have this event A. I divide the A into two parts. One is those in A which are common to B. That is A intercept B. A intercept B. A, I divide it. This is A common to B. This is A common to B complement. Maybe this is your B. All right? So A divide into two parts, those common to B and those not common to B. And they are mutually exclusive. And union together, put them together is equal to A. So therefore, applying the results that we discussed, then probability of A is equal to probability of A intercept B plus probability of A intercept B complement. All right? Now this is the most important among all this discussed so far. The probability of A union B is equal to sum of probability A and probability B. But by doing so, we double count or we include something more than just A union B. Why? Because if you look at probability of A, you have this part. Probability of B, sort of like involving this part. And this part here, we count it twice. In calculating probability of A, we consider these outcomes. In calculating probability of B, we also include this part. So this part is double count. So that's why we have to subtract it out. But what we can do is to rewrite A union B into two parts. All right? A union B, right? This is A. This is B. A union B is this whole thing. So what we write is that, okay, A union B is equal to B. This is B, right? And how can you describe this part? So that there are no overlapping. What is this part? This part obviously belongs to A. At the same time, it does not belong to B. So B complement. So intercept of it. So I can write A union B as B union A intercept B complement. And these two parts are mutually exclusive. Therefore, I can write it, substitute, like it, and then this part, all right? How to get this part? Because from property 4, we have this. Therefore, I substitute and I arrive at this. All right? Arrive at this. Probability of A union B equal probability of A plus probability of B minus probability of A intercept B. So it seems not too difficult. But then you ask yourself, what happens if I want to find out what is the probability of A union B union C? So it's like this, A, B, C. Okay, so here's the answer. So we add A, B, C probabilities together, which we count A common to A and B twice. So I have to subtract it. Common to A and C, I double count, so I subtract it. And then B intercept C also double count, so I subtract it. But by subtracting 3 times of it, I subtract too much. I have to get back those common to A intercept B and intercept C. All right? So, there are two parts. One is how to generalize this. Okay, so basically you start with adding the individual probability, subtracting the probability of intersection of any of 2 of them, and then add back the probability of intersection of 3 of them. All right? Now, if you have 4 events, a union of 4 events, then you have to continue to add back the 4th one, the intersection of 4 events. All right. The proof is not too difficult. It just write it as union of 2 events. So after you got this one, you further decompose this into what you need. All right? So finally, you get the answer. All right? A intercept B union C. All right? So it means that this set means that this consists of all the stuff, all the elements, either in B or in C, or in both of them, but we don't, okay? So it's either in B or in C. So what we need is, okay, A common to B, so that's what we do, and A common to C, all right? A common to B and A common to C. So break it into these 2 parts. Now these two, are they mutually exclusive? No, we don't know, because B and C may not be mutually exclusive. All right? So in other words, the common to B and common to A may also appear common to A and common to C. Why? Because there may be something common to both B and C. So they're not mutually exclusive. So I have to write it as probability of A intercept B plus probability A intercept C, then minus the intersection of these 2. So this means that A elements common to A and B. This means that elements common to A and C. And the common to these 2 events means that it has to appear in A, appear in B. Not only that, it also has to appear in C. So that means these elements must appear in all A, B, and C. So it's A intercept B intercept C. Now if you have trouble in working on this set thing, you just remember the definition. when you write down A intercept B, it means that we're looking at elements that in A and in B. A union B means that the elements can be in A, can be in B. Of course, there are some elements in both A and B. You remember? A union B. So this part belongs to A, but not B. This part belongs to A and B. This part belongs to A complement and B. So basically, from the Venn diagram, you know that there are three parts. All right. So what A union B means is that you have the elements in A, or the elements must may be in B, or it can be in both. All right. Okay. Probabilists use this quite often, called inclusion-exclusion principle. That is to look at the probability of an event. Yes? Derive what? How do you know how to derive? Up to you, okay. Your question basically translates whether this will be exam or not. I cannot tell you anything about whether it's with test or not. All right? Okay. But I can tell you, you have only 2 hours for your exam and 1 hour for your midterm test. Right? If you spend 120 minutes to derive one formula, forget about it. Right? Even if it's 10 marks, I will give up the 10 marks. All right? I will get the 90 marks from the rest of the questions. All right? So it depends. All right? I cannot say that there's no derivation, but you don't. If you spend a lot of time to do one question out of, let's say, maybe 10 questions, all right, then it's not worth to do it. All right. So of course, if you know everything well, then shouldn't spend a lot of time. All right. Remember, exam test is just a test to tell us how much you learned. All right. Okay. Come back to this inclusion-exclusion principle. It's just a general way to state the fact that the chance of an event which is union of n events, they are not mutually exclusive. So they can be any. They have some are mutually exclusive, some are not. So what we do is that, okay, you just add up, first of all, get the probability of individual one, but by adding all this probability, this part, then you may have this part, you have add in too much because you double count, triple count a lot. So you have tried to subtract it. So subtract this part, the probability of two events, any intersection of AI and AJ. So you get the probability and then subtract it from the first sum. But after that, now this time you get too much, too many. You take out so much. So you have to add back. Add back what? Add back the probability of intersection of three events. Then you add back too much. You have to subtract the intersection, the probability of intersection of four events. Again, too much. You have to correct it. So when to stop? Until you reach the probability of intersection of all these n events, then you stop. I cannot tell whether it is add or subtract in the last one. All right, so you can see that this is -1 to power n plus 1. All right, so it depends on the n. If n is odd, then this is plus. If n is even, then this is odd, minus that. All right, so that's. So will you ask to prove this one? How to prove it? Huh? So one possibility is n equal to a small number, like 2 or 3, right? But there's another 2, still very complicated. Have you heard of mathematical induction? Yes, use mathematical induction, but you still, the final step is still a lot of work to prove that, all right? But in fact, it may not be too much work, all right? But it's very complicated. So don't worry, you will not ask to prove this formula. But who knows, you may ask to use this formula. All right? But whatever I say, there's a probability there is 0 or 1, it's between 0 and 1. It's not 100% correct. Okay, so another properties, if you have two events, A and B, if A is a subset of B, then the probability of A must be less or equal to probability of B. All right? Now, I would suggest that you try to understand the proof. That will help you to understand the proof of other mathematical or other approach, all right, in mathematics. Now here is natural. A is a subset of B. Of course, the chance of A is less or equal to chance of B, all right? But here I try to prove that based on what? Based on all the axioms as well as the properties that we just derived, all right? So I rewrite B as the union of two events. Are these two events mutually exclusive? Can you tell? Are they mutually exclusive? Are they mutually exclusive? Yes? No? I don't know. Are these two events mutually exclusive? Yes. First one is B and A, right? The element must belong to B as well as belong to A. The second is elements belong to B. Okay, but also belong to A complement. That means the elements are not in A. How can you have an element which appear in A and also appear in A complement as well? No such thing. So mutually exclusive event. It's because this one and this one are mutually exclusive. All right? Okay, now, but because A is a subset of B, A is a subset of B, all right. Therefore, A intercept B must be A, right? Intersection of two events. So this means that it consists of all the elements. So the elements in A and in B as well. But since A is a subset of B, so there are elements in B that may not be in A. So B intercept A must equal to A. Similarly, B can be written as this one. And A intercept B, okay, this one, A union B intercept A complement. So what does that mean? In fact, if you remember, this one is not always true, this statement. This one, in fact, is A intercept B. All right? But because of the condition given to us, A is a subset of B. So therefore, A is a subset of B. Okay. This is A. This is B. Oh, sorry. Maybe I should write it later. This is B. A is a subset of B. So A at most, this is A. A may be as big as B. So obviously, A intercept B is this part only. So that's why it's equal to A. All right? So my point is, this one, rewrite it as probability of B plus probability of A. This is A, and plus probability A intercept A complement. All right? We have worked very hard to solve this part. But what's it to do with this one? So we apply probability, the axiom 1. What is this? What can we say about this probability? It must be a number between 0 and 1. So you have probability of B equal to probability A plus something. This something is between 0 and 1. So you're adding a positive or 0. So in other words, this number equal to the sum of these two, and this is a positive or at least equal to 0. So therefore, this must be bigger or equal to probability of A. All right? So it seems that intuition, I know that it is like that, like A is subset of B, of course, probability of A is less or equal to probability of B. But we show that through all this hard work, we show that probability of A is less or equal to probability of B. Because probability of B equal to the sum of two terms. One is probability of A. The other one is a number which is between 0 and 1. It's a positive number or 0. All right, so here are the examples. Example 1, I skip it. You can, example 2, okay. Example 2. So we have this poll for so a poll of statisticians. So what are their work? So A is those who do research, B is those who do professional consultation, and C is those who do data collection and analysis. First of all, what does this percent? What is 100%? When you see percent, you must ask yourself, what is 100%? So what does this 40% mean? When we say A is 40%, it's 40% of all those statisticians in the poll. 40% of them are working on the research. 64% working on consultation. And the other 36%, just 36%, okay, working on data collection and analyze, all right? So 100% means 100% of statisticians. Then here's another question. Obviously, these three numbers does not add up to 100%. Why? Why? Huh? I don't know. Why? Why does not add up to 100%? Is that a mistake? Because some statisticians can play one or more than one roles. It can do research as well as doing consultation. That means it can belong to both A and B. So in other words, A, B, C are not mutually exclusive groups. All right? So that's why it does not add up to 100. Okay, here is another question. So A, B, C are not mutually exclusive. Why it's not mutually exclusive? Because it does not add up to 100. If all this percentage add up to 100, then they are mutually exclusive. You must belong to one of these groups, not belong to more than one of these groups. All right? Now, but my question is, if I belong to one of these statisticians that are being polled, so do I have to belong to one of these groups? Can I do more? Maybe I can give tuition. D, given tuition. So what I mean is that A, B, C, these three groups are exhaustive. All right, collectively exhaustive. That means any statisticians must belong to one or more of these three groups. All right. So basically, what I'm trying to say is that you make sure that you understand it properly. That this is the group of statisticians. All right. It divides into three parts. If it's like that, they're mutually exclusive. But what now I have is, okay. Maybe I better A, B, and C. So this together is my group of statisticians. All right. So some of them belong to A, some of them belong to B, some of them belong to A intercept B, some belong to A intercept B intercept C. This part belong to A intercept B intercept C. All right. But you have, maybe from here we don't have this information whether A, B, and C are exhaustive events, exhaustive group. That means combine them together, put them union. That is. My question is A union B union C, is it equal to the sample space? All right. So in order to proceed, we have to assume that. Otherwise, we cannot. All right? We cannot proceed. In other words, knowing all this probability, all this percentage will not tell you whether A union B union C is equal to the sample space. So I have to make such assumption. All right? Otherwise, I cannot proceed. Okay, so all this tells you the probability. So this one, probability of A intercept B intercept C, all three activities equal to 0.1. All right. And then this one is probability of A, both A and C. So A intercept C is 0.15 and so on. So now you are asked to find out what is the percentage that do both B and C. So you are supposed to find this one. So how to find this one? So we try to set an equation, involve this one as the only unknown, and then solve the equation. So what are the equations that we can set? We can set up the equation like this. This one is equal to 1. We assume that A, B, and C are collectively exhaustive. So this is the property, and all these are known to us except this one. So now we can solve this equation. So that's why we have to assume this is equal to 1. If this A union B union C is not the whole sample space, then we are in trouble because now we cannot have a second equation that involves probability of B intercept C from the information given to us. So we have to make this assumption. This equal to 1. So usually, if you are doing survey or you're doing, so we should make sure that there should be one category that cover any other statisticians, in this example, any other statisticians who do not work on these three areas. All right, there's a fourth one. So D, none of the above. And what is the percentage? 0. All right, then you will know that means these A, B, C are mutually, collectively exhaustive. Okay, so we solve it. The answer is 0.18. 18% are working on B and C. Okay, example 3. So here I just want to emphasize that we have 0, 1, 2, 3, 4, 5 or more. Okay, and this one is the one that I mentioned. So you have a gas station or a pump, and then in a certain period there are cars visiting or need to fill the tank, all right, with gas. So there may be within this period no cars or one car, 2, 3, 4. Then there can be 5, 6, 7, 8, and so on. Maybe there are 100 cars arrive during that period. So to make it simple, we just assume that the last one, 5 or more, that includes 5, 6, and any number bigger than 5, 5 or more, as one event. All right? So we asked how to find the probabilities. All right? Now, first of all, check. Does all this add up to 1? Add up to 1. If not, something wrong. Because we're supposed to cover all possibility. No car there to fill up the tank. Or 5 or more, including 5, 6, 7, 8. So every number will be covered. So it should add up equal to 1. The probability should add to 1. So more than 2 cars means the number of cars can be 2 or more than 2, 3, 4, 5 or more. So basically only 3 events. Right. So you can got A3, A4, and A5. A5 is 5 and more. At most 4 means it can be 0 car, 1 car, 2 cars, 3 cars, and 4 cars. what is the probability of union of all this. That is for part B. Are these mutually exclusive events? Yes. If the number of cars is 2, it cannot be 3 in the same period. All right, so they're mutually exclusive. But of course, you can also consider 1 minus probability of A0 union A1. That's another way to do it. Find a complement event and then subtract from 1. All right, so this is example 3. Right. So you must, okay, I gave you the solution, but then you have to understand it. So first of all, we translate this statement into the events. More than 2 means 3, 4. Now this is not 5 cars. This is the event with 5 or more cars at the pump. All right? Or at the gas station. And next, from here to here, why I can just add the probabilities? Because A3, A4, and A5 are mutually exclusive events. So that's why I add up. Then now I get from here to here is use the information given in the questions. Oh, here's a tips about exam, right? Whatever you find in the questions, information in the question, almost 99% you have to use it. If you don't use them, then it's likely that you may miss something. All right? Use all the information given to you. But don't add in information is not given there. Except now just the one that I assume that A, B, C, the three types of work for statisticians is supposed to be any statistician must work on one or more of these areas. All right? No other areas. So that's the assumption I make. But usually you try to use the information and don't add in your information. All right? So here from this to this, I use the information given in the question. So 4 cars is point X3. Okay? Alternatively, I also use a different approach. I got the same answer. So I feel more confident that I'm getting the correct answer because I use 2 different ways and I get the same answer. But of course, it may be same wrong answer. So there's a possibility, talking about probability. So there's still possibility that you are wrong. All right? Even the 2 approaches give you the same answer, maybe the same wrong answer. Okay, this is a very, okay, I think you can work it yourself. Yeah. This is the next 2 examples is very interesting. Example 5. I don't know whether you heard about it. Go to a room or party trick. If there are at least a very big party, 50 people there, all right, then you claim that, okay, 2 people sharing the same birthday. There are 2 persons, at least 2 persons share the same birthday. So how likely it is? All right, for 50 persons in the party, the chance is very high. If you flip to the next page or next 2 pages, you have the answer. But the problem, you have to know how to get the answer. All right. So here is the questions. If you are n people in the room, so what is the chance that at least 2 people with the same birthday? Remember, same birthday means that you can have 2 have the same birthday 1st of January. Maybe 3 of them have the same birthday 1st of January. You may also have 2 persons 1st January as birthday, another 2 have December 31st as the birthday. That means 2 different birthdays, 2 different days for the same birthdays. So it's very complicated headache. How do we figure out how many people have the same birthday and different days left? But if you think it the other way, so what you need to do is to figure out there are no persons among this group with the same birthday. It will be much easier to work that way. No 2 persons share the same birthday. So, okay, So assume that each day is equally likely and assume that there are only 365 days, no leap years, no 366 days. So each one has their own birthday, so all the possible number of permutations is 365 raised to power n, because the first person has 365, the second person also has 365, and so on. So they're all together n of them. All right, so this is the number of possible ways of the arrangement of the birthdays. All right, so now we ask ourselves, so pick one person, the birthday, any one day of this 365. Pick the second person. Now this person, the birthday, we want it to be different from the birthday of the first one. So left with 364 choices for it, right? Then after these first two persons, the third one will be 363, and so on until you reach 365 minus n minus 1. Because for each factor that you included in, it should be subtracted by n, by the position minus 1. So the second factor, minus 1. Third factor, minus 2. So the nth factor, minus n minus 1. All right? This one, 365 minus 0, 365 minus 1. So this one, the nth factor is 365 minus n minus 1. So divide by the possible ways. So write it in a nice way. It will be like this. So this is the probability of having, this is the probability of having no two persons share the same birthday. Subtract it from 1, so this is the probability of at least two of them share the same birthday, or more than 2, or more than 2 days of the same birthdays. All right? So to appreciate it, let's look at this table. 50 persons. The chance that you will find 2, you will find 2 is 98%. All right? It's very high chance that you will find 2 with the same birthday. All right? So even if you have 23, the chance is almost half that you will find 2 have the same birthday. So in other words, it's not too difficult to have people share the same birthday. Even for a small group like 23, the chance is 50%. All right? Okay. There's another type of birthday problem called inverse probability. So you ask yourself, 23 or 50%, the chance is so high with same birthday. So now I ask, what's the chance that I will get people have the same birthdays as my birthday? Same as my birthday. Now it's not any date, but it has to be my birthday. All right, so that's the problem. All right, so I want to figure out how big the group is in order to have the same birthday chance of getting someone have the same birthdays as my birthday with a probability bigger than 0.5. All right? So this is the probability that you get no one with the same birthday as yours. Isn't it? Because the other guy must have other birthday, not the same day. Suppose my birthday is 1st of January. So the other guy, second guy, cannot have 1st of January's birthday. Third guy cannot have. All the n guys cannot have. So this is the probability of people, the probability of having n persons all have a birthday different from mine. But they can have the same birthday among themselves, but different from mine. No one in this n persons or n minus n persons are having a birthday same as mine. So now 1 minus it, all right, is the probability that I will get someone with the birth, at least one, have the same birthday as mine, 1 minus it. I want it to be greater than 0.5. All right? So I said about inequality, I have to solve this inequality. And there are two problems here. It's not an equation, it's an inequality. So when you move around, multiply a factor or divide a factor, you have to remember switch the direction of your inequality. That's the first thing that you have to remember when solving inequality. Second, the unknown n is in the exponent. It's not ordinary inequality. So what you have to do, you have to write it like this. Move this one, so it's 1 minus 0.5 greater or equal to 364 over 365 to power n. All right? So this one is just 0.5. So pull it down, the unknown n, to the ordinary position, not in the exponent. How to do it? Take log. Take log. Take log. So it is log of 0.5 greater or equal to n times log 364 over 365. All right? So now n is, how come the inequality is reversed? According to this one, if I divide it, it should be log 0.5 divided by log 364 over 365, right? Why the inequality reverse? What negative? Because you divide by log 364 over 365. 364 over 365 is less than 1, right? Look out to your calculator, press log, what number less than 1? A decimal place, 0.9. So you get negative numbers, right? Log 1 equals 0. No matter what base you are using, log 1, base e, base 10, base 2, log 1 is equal to 0. So a number less than 1 will give you a negative number. All right? So that's why you have to reverse inequality, and that is the answer. Wow, you need 252 persons in order to get someone has the same birthday as yours. Not 50. Previously it's 50 because that one is not my birthday. Now I want to specify it's my birthday, same as my birthday. I don't care about whether they have same birthday on other days, but I want to know what they have the same birthday as mine. I need 252. And this number only gives you half of the chance that you will find someone have the same birthday as yours. All right? So here just a remark. All right? So this particular problem is referring to your birthday, while the previous example 5 is referring to anyone, any date, so long they share the same birthday. And it can be more than just one day they have the same birthday. All right? Okay. Yeah, I think I have to stop here. And then this Thursday we start this session on sample space, having finite outcomes. So we stop here. So remember to do your registration for tutorial and start working on your tutorials.